Now we go to conjugate harmonic functions. It is imperative that we note that a pair of functions of both x and y, that is functions u and v, satisfying the Cauchy-Riemann equations, we call them conjugate functions. And then thereafter, we say a function that satisfies the two-dimensional Laplace equation is a harmonic function. Therefore, if we have our f of z equal to u of x y plus j v of xy, analytic and satisfying the Cauchy-Riemann equations, then both u and v are called conjugate harmonic functions. So if our function f of z is analytic, satisfying the Cauchy-Riemann equations, then both u and v are conjugate harmonic functions, noting that they become harmonic functions if they satisfy the Laplace equation in two dimensions. And they become conjugate functions if the function itself satisfies the Cauchy-Riemann equations. Let's do some examples. We are asked to determine the harmonic conjugate functions for the given functions. Now in this case, we've been given u. And u is a function of both x and y, and it's xy minus x plus y. Note that we had said conjugate harmonic functions, they will only become conjugate harmonic functions if the function, the mother function f of z, is analytic and satisfies the Cauchy-Riemann equation. So that means both u and v must satisfy the Cauchy-Riemann equations. Hence, immediately we are asked to find the harmonic conjugate functions. The first assumption is that the function, the mother function, is analytic and both u and v satisfy the Cauchy-Riemann equations. Hence, the first step we need to recognize are the derivatives that ought to be equal in terms of Cauchy-Riemann equations. So the first one is du over dx equal to dv over dy. And we've been given u to be xy minus x plus y. Now du over dx, that means we hold y a constant, then we differentiate u with respect to x. Therefore, we'll have y minus 1 as our answer. And because this function u satisfies the Cauchy-Riemann equations, this y minus 1 must be equal to the derivative of v with respect to y. In order for us to find v, which is the conjugate, harmonic conjugate of u, then we need to integrate. Note that we've got dv over dy here. In order for us to find the original function, we have to integrate with respect to y in this case. So because we already have dv over dy, so we integrate with respect to y in order for us to get the original function v. Remember, the derivative and the integral, they are antiderivatives of each other. All right. Then that means on the right hand side, we integrate y minus 1 with respect to y. Note we're still using partial integration. Then The integral of y will be equal to y squared over 2, and the integral of -1 is negative y. But then we cannot say plus c because we don't know whether f of x is a constant or not. So because we're integrating with respect to y, then we say plus the function of x. The next step is to use the second Cauchy-Riemann equation, du over dy equal to negative dv over dx. We already have the function u, and we already discovered the function v. So we go to those two equations and find the derivative of u with respect to y. Please check with me whether the answer is x plus 1. And the derivative of v with respect to x only has the function f of x only that can be differentiated. So hence we have the negative of f prime of x. Then make f prime of x the subject, and then find f of x. Note, when you've got the derivative, you want the original function, you integrate. So that means we integrate f prime of x with respect to x, and we integrate the right hand side with respect to x as well. So we get f of x on the left. The integral of negative x is negative x squared over 2, and the integral of -1 is negative x plus c. We can say plus c at the end. Then we take this function and we go and substitute where there is f of x in the formula for v. So therefore we have y squared over 2 minus y minus x squared over 2 minus x plus c as a formula for the harmonic conjugate of u. Now in this exercise we've been given v. Remember in number 1 we're given u, now we're given v. Now let's see how we're going to move forward. Remember again, we are looking for the harmonic conjugate function of v, which is u. So we use the Cauchy-Riemann equations for us to achieve that. So the first Cauchy-Riemann equation is du over dx equal to dv over dy. And then we go to the formula given for v. We find the derivative of v with respect to y, which is 2y plus 1. Remember that we hold the other variable a constant. So we allow it to behave as a constant because we're doing partial differentiation. So that means the derivative of negative x squared is 0. Then if you removed that bracket there, you'll have 2x minus 2xy. So that means the derivative of 2x will also be 0. And then you will be left with the derivative of negative 2xy. And then that will give you negative 2x. So now we have du over dx equal to 2x plus 1 minus 2x. Remember, we have v, we are looking for u. So that means now we integrate with respect to x because we're differentiating u with respect to x. That is why we integrate with respect to x. So we'll integrate with respect to x, left and right hand side. Hence, we see dx instead of dy as it was the case in number 1. Then thereafter we do the integration. The integration of du over dx with respect to x is just u. And then the integral of 2y with respect to x is 2xy. The integral of 1 with respect to x is x. And the integral of negative 2x is negative x squared, because it's going to be negative 2x squared over 2. 2 and 2 will cancel. Note, because we're integrating with respect to x, we say plus f of y. Function that we add takes the other variable. Okay, then we go to the second Cauchy-Riemann equation. Du over dy is supposed to be equal to the negative of dv over dx. Du over dy, we go to u. U is here. We've already found its formula. Differentiate with respect to y. That means we'll get 2x plus the derivative of f of y. And then equal to the negative. And then I use the brackets because I've got more than one term for v. Then we differentiate v with respect to x. So that means we'll have negative 2x plus 2 minus 2y. And then please check. And then you multiply that with a negative. That means remove the bracket altogether. And then make f prime of y the subject. So the right hand side will be 2x minus 2 plus 2y, and the right hand side is 2x plus f prime of y. So if we make f prime of y the subject, we get minus 2 plus 2y. Integrate both sides to get f of y. Then we'll have f of y on the left. Integral of negative 2 with respect to y will be negative 2y. And the integral of 2y is 2y squared over 2. 2 and 2 cancel. That's why we have y squared plus c. And then we go back to the formula for u. We substitute in place of f of y the expression that we got here for f of y, so that we get a full expression of u. For number 3, we have been given u. We use again the first Cauchy-Riemann equation, du over dx equal to dv over dy. Then we find the derivative, giving us 4x cubed minus 12xy squared plus 1. And then we are trying to find v, and v here is differentiated with respect to y, so we integrate with respect to y. Then please check whether you're going to get the same answer for v that I got there. And remember, when we integrate with respect to y, we add f of x instead of c. And then we go to the next Cauchy-Riemann equation, du over dy equal to negative dv over dx. Du over dy, we go back to the original equation. Differentiate u with respect to y. That gives us negative 12x squared y plus 4y cubed. And then equal to the negative of the derivative of v with respect to x. That gives us 12x squared y minus 4y cubed plus f prime of x. And then we solve for f prime of x, and in this case we got a 0. Then that means f of x is equal to 0. Remember, the derivative of a constant is always equal to 0. So therefore our v is that expression. Please continue to check whether we've done the correct solutions. Number 4. Number 4 now, still we are asked to determine the harmonic conjugate of v. That means you are asked to determine u. And then thereafter, you are asked to find the function f of z such that f of negative 1 is equal to 4 minus 2j, and we're using the simplest form in terms of z. So we're still going the same route using the harmonic conjugate, knowing fully well that u and v satisfy the Cauchy-Riemann equations. We go that route yet again. First equality is that dv over dy is equal to d over dx. We go to v. The derivative of v with respect to y only gives us 2x. Then thereafter we find u, which means we integrate du over dx with respect to x, and we integrate 2x with respect to x. And then this is what I got, x squared plus f of y. Thereafter, we go to the second equality, dv over dx equal to negative of du over dy. And then v, the derivative of v with respect to x, it's 2y plus 2 equal to the negative of the derivative of u with respect to y, which is just f prime of y. Therefore, that means we get f of y equal to negative y squared minus 2y plus c. And we got u equal to x squared minus y squared minus 2y plus c. Please recall, first we are asked to find the harmonic conjugate of v. We got that, which is u. But then the question continues to say, hence, find the analytic function f. And then we have a specific value for z that we have to use in order for us to calculate c. So now we've got u and we've got v. Let's find f of z, and then thereafter find the constant c using the specified value of z that has been given to us. You know f of z is equal to u plus jv. I just substitute in u, it's what we have, plus j times v, which is that. First things first, remove the brackets. And I took c to the end, remove the brackets, and then rearrange. So I know immediately we have x squared and negative y squared. That means the middle term is j to xy, because that is x plus jy all squared. It is given by those three terms. And then the next two terms that we have is minus 2y plus j 2x. We need to also recall the negative represents j squared. Negative 1 represents j squared. So that means for the next two terms, we've got a common factor, which is positive 2j, so that we can have x plus jy. Remember, what we're trying to find is to make sure that our f is in terms of z. So whatever term that we come up with, it must have x plus jy, which is z. So we end up with f of z equal to z squared plus j 2z plus c. Then we have been given a specific value for z, and when you substitute it to the function, it gives us 4 minus 2j. So what we need to do in our function that we've discovered here, substitute negative 1 in and equate that to what has been given to us so that we can be able to solve for the value of c. So all in all, we've got that 4 minus 2j equal to, in place of z in our function, we substitute negative 1 in and then simplify, and we got c to be equal to 3. Please check the steps and make sure that our calculations are on point. Please recall again, once a specific value of z has been given, you need to change function and write it in terms of z, and then thereafter substitute the given term and solve for the constant. Here are some exercises based on analytic functions and harmonic conjugate functions. Please do them and check and continue to check your answers. Now we go to the complex series, starting with the power series. And in the power series, we'll be mostly using the binomial series, but then the format of the power series, the standard format, is given by the sum of an into z minus z naught all to the power n starting from 0 to infinity. The coefficients an are either real or complex, and z naught is sometimes called the center, or it's just a fixed point in the complex plane. Also, we need to recall that in a geometric series of the form sum of z to the power n starting from 0 to infinity, the sum of n terms is given by 1 minus z to the power n all over 1 minus z. And note that this sum to n terms converges if the modulus of z is less than 1. That means the region of convergence is a circle centered at 0 with radius 1, and it converges to the limit 1 over 1 minus z as n approaches infinity. Hence, you'll find in some books they just simply write s sum to infinity is equal to 1 over 1 minus z. Is because this series converges to 1 over 1 minus z as n approaches infinity within this circle of radius 1 centered at 0. And please note that this series diverges outside the circle. That means when the modulus of z is greater than or equal to 1. So that means this series does not converge on the circle itself. It converges within the circle. This has just been summarized by that statement, and R is known as the radius of convergence. Also, we reminded that the binomial series expansion is given by that formula. Note the first term should be 1. It's 1 plus z all to the power n on the left hand side. Right hand side is 1 plus nz plus the third term is n into n minus 1 over 2 factorial times z squared. Note that to simplify matters, if you've got 2 terms in the numerator, then it means you are dividing by 2 factorial and the power of z is 2. If you've got 3 terms like n into n minus 1 into n minus 2, there are 3 terms there, then that means you are dividing by 3 factorial and the power of z is 3. And note also, it might not be z, but just a function of z that is in that term. So 1 plus a function of z all to the power n is the one that is valid within the center with radius 1 and centered at 0. That is a circle of radius 1 centered at 0. So again, we are noting that the region of validity of this function is modulus of z less than r. Then our expansion using the binomial series will take the form of the summation of an z to the power n from 0 to infinity. If the function is valid within the circle of radius r, then the expansion will have positive powers of z. Secondly, if the region of validity has been given to be greater than r, then in order for that function to converge, the expansion will make sure that the powers of z are negative. Hence, we have the expansion being of the form an divided by z to the power n, summed from n equal to 0 up to infinity. Once more, sometimes we're given that the region of validity is a circle not centered at 0. That means you will be given the value of the center. Note it's z minus z0, where z0 is the center of the circle, and less than r. So that means we still have a circle. The region is within that circle, centered at z0. Then the expansion will be of the form, taking note that z minus z0 must feature in all the terms in the expansion. So you'll have an into z minus z0 all to the power n, summed from n equal to 0 to infinity. Once the region of validity has a different center from 0, note that all the terms will have that expansion with that term z minus z0. Let's do some examples. But before we do examples, let's just plot the region of convergence for a power series so that we get to understand how it looks like. So the region of convergence of a power series is as is given in the diagram. Note that we've dashed the circumference of the circle because the region of validity is less than. It does not have the equality. So the region of convergence is within the circle. On the circle itself, the radius is 1. Let's do some examples. Firstly, we've been given one function here. F of z is equal to 1 divided by z minus 3. The first thing that we note is the region of validity. Modulus of z is less than 3. And we had said once we've got a less than, that means all the powers of z will be positive. We'll have an times z to the power n in our summation series, n starting from 0 to infinity. So we need also to recall, in order for us to use the binomial series, the left-hand side has to be 1 plus z all to the power n. So now here we've got 1 over z minus 3. So all in all, in order for us to have a plus 1, we need to take out negative 3 from the denominator. The reason why we're taking out negative 3, Firstly, it's because we've got a less than. There is our inequality. Secondly, we need to have a positive 1 in there in order for us to use the formula for the binomial series. So we take out -3, the denominator. Then that means the second term that has got z is negative z over 3. So we know we've got 1 plus a z term or a z function. That means it qualifies to be expanded in terms of the binomial series. So we rewrite it properly. So we've got -1 over 3 outside, and we've got 1 plus the negative of z over 3, all to the power -1. Now note that n in our case is -1. Then we use the binomial series expansion formula. We just substitute in n is equal to -1. In place of z, we have -z over 3. So note that we have a -1 over 3 on the outside. So we take it down, and then we open the bracket. The first term in the binomial series is 1 plus n times the z term. N is -1. The z term for our function is -z over 3 plus the next term, -1, -2 in the numerator, divided by 2 factorial, and then we'll have -z over 3 all squared. Plus, you've got -1, -2, -3 in the numerator, divided by 3 factorial into -z over 3 all to the power 3 plus dot, dot, dot. Note, you need to write those 3 dots, showing us that this is an infinite series going all the way to infinity. Then simplify the terms, removing the brackets. Please make sure that the signs are correct. So we've got z over 3 is the second term. -1 times -2 is +2, and 2 factorial is just 2 times 1. Then you will have -1 squared, which is positive, and then we'll have z squared over 9 is the only term representing the third term for our simplification. And then please check that you'll get z cubed over 27 plus dot, dot, dot. And then the last step is to multiply out by -1 over 3. Please note that once you've written your answer, the region of validity must be written as well. We go to B. We're still expanding the same function, f of z equal to 1 over z minus 3. Please recall that once we have a different center, which is not 0, in our case, our center is 2, means all the terms in our expansion must have z minus 2. So because we had z minus 3, how do we have z minus 2? We know -3 is just -2 minus 1. That's the simplest thing that we can do. And then thereafter, remember that the first term in the binomial series should always be +1. So we take out the negative. Hence, we have the negative of 1 minus z minus 2 all to the power -1. And n equal to -1. And then thereafter, we do the expansion. Just simply simplifying this whole thing, it gives us 1 plus z minus 2 plus z minus 2 all squared plus z minus 2 all to the power 3. And then thereafter, we multiply by that negative. Please remember, once you've written your answer, don't forget to write the region of validity. C. Now the modulus of z is greater than 3. Recall that we had said once we've been given greater, then it means we have to divide by z to make the function to be valid within the given region. So all in all, because we have z minus 3, what you need to do, take out z. So we take out z, we'll be left with 1 plus negative 3 over z. So our z function now is negative 3 over z. Then thereafter we do the expansion. Please keep on checking whether we've done the correct thing and check the signs as well, whether they are correct. And then don't forget to take down that 1 over z, because we had 1 over z that you took out, so that at the end you multiply out, and after multiplying, write also the region of validity. So when you have the modulus of z greater than your r, you take out z from the denominator. When you've got the modulus of z less than r, you take out the constant from the denominator. If you've got the modulus of z minus z naught less than r, then you make sure you manipulate the function such that you have that z minus r that has been given to you in the condition of the statement. Here are some exercises that you can attempt to do. Please recall that in the previous exercises that we've been doing, we had the power of z minus 3 to be 1. In this case, it's 2. So our n is negative 2, because remember, you're going to take this up. And note here, the condition for number 1 is greater. So that means what do? You take out z. But note, it is not just z to the power 1, it is z to the power 2, because that squared also is valid for that z. So that means in your denominator, you take out z squared. Attempt and let's see. And also here, we've got z minus z naught less than pi over 2. So all your terms must have z minus pi over